My dear students, today's lesson is thermal stability of metallic 2 carbonates. In this lesson, we are going to discuss atomic and cationic sizes of group 2 elements, resonance structures of carbonate ion, temperatures to decompose carbonates, and finally reason behind different temperatures. So let's begin. The very first point is atomic and cationic sizes of group 2 elements. The group 2 elements are beryllium, magnesium, calcium, strontium, barium and radium. Radium is a kind of radioactive element, so it is kept out of consideration. And the ions are beryllium 2+, magnesium 2+, calcium 2+, strontium 2+, and finally barium 2+. We know from top to bottom along a column in the periodic table, atomic sizes increase, and at the same time ionic sizes increase as well. So we can write order of atomic sizes: barium, strontium, calcium, magnesium, and then beryllium. That means the size of barium is the most and the size of beryllium is the least in this column 2. And order of cationic sizes: barium 2+, strontium 2+, calcium 2+, magnesium 2+, and finally beryllium 2+. That means barium 2+ cation, its size is the most, and the size of beryllium 2+ is the least in this series. Let's see the next point. Now the point is resonance structures of carbonate ion. This is carbonate ion with 2- charge. That means this is di-negative charge. The structure formula of this carbonate ion is oxygen double bond. This is 1- and this is another minus. This is the structure formula of carbonate ion. And in this case, what happens, let's see, that is here there are 2 electrons. One electron of oxygen itself and another electron came from metal. For this additional electron, this minus charge is put here. This is the minus charge for this additional electron. So here there are 2 electrons actually. Here one pair of electrons. This pair of electrons turns into bonding pair, and at the same time this bonding pair of electrons turns into lone pair of electrons, because here the electronegativity of oxygen is greater than carbon. Carbon's electronegativity is 2.5, oxygen's electronegativity is 3.5. So oxygen attracts this covalently bonded electrons towards itself, and this structure is obtained. That is, this is minus charge, double bond turns into single bond. Here single bond turns into double bond, and it remains as it is. So these two structures are resonance structures, and resonance structures are shown with this double-headed arrow. Another resonance structure is this lone pair of electrons turns into bonding pair of electrons. At the same time, this bonding pair of electrons turns into lone pair of electrons, and this structure is obtained. That is, this is single bond, it turns into double bond, again it turns into single bond with this charge. That means all the oxygen atoms are carrying negative charge. This oxygen, and in this structure this oxygen. Simply, all three oxygen atoms are carrying negative charge. An average structure is obtained. That is, oxygen, here carbon, here oxygen, here oxygen. That means this is not completely single bond, a partial double bond. This is not completely single bond and not completely double bond, a partial double bond. Similarly, this bond as well, and with partial negative charge. This structure is called hybrid structure of carbonate ion, and these three structures are called resonance structures. So here, what is resonance? The movement of electrons within a molecule through bonds is called resonance. That means simply movement of electrons in a molecule is called resonance. And then resonance structures. The structures obtained through movement of electrons are called resonance structures. And finally, hybrid structure. This is hybrid structure of carbonate ion. So what is hybrid structure? Hybrid structure is defined as the average structure of two or more resonance structures is called hybrid structure, and this is the hybrid structure of carbonate ion. This is all about resonance structures of carbonate ion. Let's see the next point. Now the point is temperatures to decompose carbonates. That means here group 2 elements metallic carbonates, and those are beryllium carbonate, magnesium carbonate, calcium carbonate, strontium carbonate, and finally barium carbonate. To decompose this carbonate, heat is required. That means beryllium oxide, here it will be beryllium oxide and carbon dioxide. So to decompose these carbonates, heat is required. These compounds are heated at a specific temperature. What are those temperatures? Let's see. To decompose this carbonate, 100 degrees centigrade temperature is required. In this case it is 540 degrees centigrade. In this case this is 900 degrees centigrade. For strontium carbonate this is 1290 degrees centigrade, and in case of barium carbonate this is 1360 degree centigrade temperature. That means different carbonates, different temperatures are required. Now we have to know what is the reason behind different temperatures. Let's try to learn the reason behind different temperatures. The point is now reason behind different temperatures to decompose carbonates. From the previous point we learned for beryllium carbonate it requires 100 degrees centigrade temperature to decompose, and for barium carbonate it is 1360 degrees Celsius temperature. That means to decompose this compound beryllium carbonate 100 degrees Celsius temperature, then we get beryllium oxide and carbon dioxide. And for barium carbonate the temperature is 1360 degrees Celsius, which is comparatively very high, and the products are barium oxide and carbon dioxide gas. So these are the carbonates of same column, but to decompose these different carbonates different temperatures are required. Now let's try to learn what is the reason behind this. Now let's see the structure formula of beryllium carbonate first. This is nucleus of beryllium and this is carbonate ion. This is beryllium 2+. We already learned that beryllium is smaller in size in this group, and this is a di-positive ion. That means in this case the charge density is very high. For this reason its polarizing power is very high as well. So for beryllium carbonate, carbon dioxide is polarized excessively like this. It is polarized on a large scale. Because of its high charge, it can polarize carbonate ion to a greater degree, and at one stage this bond, oxygen carbon bond, becomes weaker and breaks with low temperature, and finally carbon dioxide breaks free, leaving beryllium oxide like this. Beryllium carbonate with low temperature, because in this case carbonate ion is polarized on a large scale. Beryllium oxide and carbon dioxide breaks free. But in case of barium carbonate, barium which is bigger in size with 2+ charge, and this is carbonate ion, this is minus, partially minus charge, partially double bond, partially double bond. This is barium 2 plus. Barium 2 plus is bigger in size with 2 plus charge. That means in barium 2 plus charge density is comparatively low, and for this reason this barium 2 plus cannot polarize this carbonate ion as much as what happens in case of beryllium carbonate, and that is why this bond doesn't become weaker like this case. So for barium carbonate it requires high temperature, that means 1360 degrees Celsius temperature, then only this carbonate ion breaks free, leaving barium oxide. So this is the reason of different temperatures. That means in beryllium carbonate ion is polarized on a large scale. That is why in this case low temperature is required to free carbon dioxide. But in case of barium carbonate ion is polarized on a limited scale. As a result, here high temperature is required to produce carbon dioxide gas. So this is the reason, simply high charge, more polarization, low charge density, less polarization, more polarization, less heat is required, low polarization or less polarization, a high amount of heat is required to produce carbon dioxide. So thermal stability order is barium carbonate, then strontium carbonate, then calcium carbonate, magnesium carbonate, and after that beryllium carbonate. This is the thermal stability. That means barium carbonate is more stable compared to beryllium carbonate. This is all about thermal stability of carbonate. No more today. Thank you very much. Take care.